The next example we're going to look at is using long division before integration. In example 5, we want to find the antiderivative of x squared plus x plus 1 divided by x squared plus 1. This is a rational function. It's because it's the quotient of two polynomials. And what makes this one a little bit different than some of the other ones we've had in the past is that the degree of the numerator is at least equal to, or it could perhaps be more than the degree of the denominator. And anytime that happens when you're trying to do an integration, we want to do long polynomial division first in order to simplify and reduce this thing. So to begin, I want to rewrite the integrand by doing a long division. I want to divide x squared plus 1 into x squared plus x plus 1. X squared goes into x squared one time. So I write the constant 1 on the quotient line. I then take that quotient value, I multiply it by x squared plus 1. Writing everything under the like terms. We go ahead and subtract. X squared minus x squared cancels. 1 minus 1 cancels. And so we get x. So we can write this answer as quotient plus remainder over divisor. So this allows us to simplify and rewrite that integrand. So this is equal to, via polynomial division, 1 plus x divided by x squared plus 1 dx. And now we're going to be able to find this antiderivative. We can split apart using our properties of antiderivatives. I can do the integral of the first term. That's going to be 1 dx plus the indefinite integral of the second term. For this one here, this is just the integral of a constant. That's going to be the constant times x, so we get x plus, for this one here, we can do a U-Substitution. Let u be the denominator, so u is going to be x squared plus 1. Du is going to be 2x dx. So we need an extra factor of 2 on the inside. I can multiply by 2 if I put a 1/2 on the outside. So we're going to get 1/2 the antiderivative of 1 over u du. We know that that's going to be 1/2 times the natural log of u and then plus c, which is equal to x plus 1/2 the natural log, back substituting, of x squared plus 1 an absolute value plus c. So this would be our final answer. Just a couple comments to make about this. Again, when you're going to need to do the polynomial division is whenever the degree of the numerator is equal to or higher than the degree of the denominator. Also, if you look overall, whenever I did these two antiderivatives, okay, we only need to ever include one constant of integration at the end here. Because at the end of the day, if I get one constant of integration from the first antiderivative, and if I get a second constant of integration from the second one, you can kind of combine those two, so you just end up with one constant in total in the final expression. So I just kind of chose to write it at the very end when I did my second antiderivative. The other thing, and this will come up on occasion, and you just got to kind of be on the mind for it. If you look at x squared plus 1, whether it's from the graph or just analyzing it, x squared plus 1 is always greater than 0. Okay, in particular, it's always greater than or equal to 1. But what that means is that the inside of that natural log is always going to be positive. So for this particular situation, you can actually eliminate and get rid of the absolute value bars. They're not going to be necessary. Okay. We weren't able to say that for some of the other examples we did. If I just kind of scroll back for a moment, for example, if you look at this antiderivative here, 3x plus 2 will be negative for certain values of x. For example, if you plugged in like x negative 1, x negative 2, etc., the inside of that natural log would be negative, and so here you absolutely have to have the absolute value bars, because for certain values of x, the quantity 3x plus 2 could be negative. Likewise, if I come over here, this expression, x squared plus 2x, that will also be negative for certain values of x. For example, try it. Plug in x equals to negative 1, and that will give you a situation where that inside of that could be negative. So again, here you have to keep the absolute value bars, but with this one here, because x squared plus 1 is positive, we can kind of eliminate and drop them. Let's take a look at another example. And the next example gives another instance in which the use of the log rule is disguised. In this case, a change of variables helps in order to apply the log rule. So we look at it and we say, okay, well, what might we try? We have kind of two competing ideas for what we might want to do for our U-substitution. We've seen before that if you have something that's like u to a power, oftentimes it's kind of helpful to let u be that thing under the exponent. Or we've seen from the last couple examples that sometimes it's convenient to simply let u be the entire denominator. Okay. The question is, which one should we do? Well, if I try the first u sub, that would give us a du, which would be equal to dx. And we would be off by more than a constant there. So that would be difficult, but it's not overcomable. For this one, if I try my du, I'd have to use the chain rule. And this expression here looks a lot further off from what this one than did our first one, than did our first substitution for u. So let's try this out. Let's let u be x plus 1. We're going to let du be dx. This is the case where we're actually off by more than a constant. So my dx here, my du, is equal to dx. This is the scenario where you want to take your substitution and actually solve for x and solve for dx. If I solve the first equation for x, I just subtract 1 from both sides, and I would see that x equals u plus 1. And it's already solved for dx. Dx is simply equal to du. With this substitution, here's what we're going to get. We're going to have the antiderivative of, first of all, the 2 I could factor out, constant multiple rule. Wherever I see an x, I can put u minus 1. Our dx I can swap out for du. And then u was x plus 1, so this is going to be now u squared. So we were able to get the substitution to work. From here, what we can do is we can split apart the numerator. I can write it as u over u squared minus 1 over u squared du. This is going to be 2 times the antiderivative. This is going to be 1 over u, which we know is going to integrate to a natural log. And this part here, I can rewrite it as u to the negative second power du. And to that term, we can apply the power rule. So we get the following. The antiderivative is going to be the natural log of the absolute value of u minus, if we add 1 to the power, we get negative 1. We have to divide by that new power, negative 1, plus c. This is equal to 2 times the natural log, the absolute value of u, plus 1 over u plus c. And now we can just kind of simply go ahead and back substitute. Everywhere we see the expression for u, we know that u was x plus 1. So it's 2 times the natural log of the absolute value of x plus 1 plus 1 over x plus 1 plus c. And that would be our final antiderivative.